Okay, so today we're talking about real zeros of polynomials and how to find them. So we have the factor theorem that says let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c equals 0. Now this is the reason that we call our solutions zeros of the function. When you plug a given r value or c value, in this case, into the function and you get 0, that means that when we graph it, at that c value, the y value is 0, and that, of course, makes it an x-intercept. We call these our roots and our solutions. All these different words for these same values for different reasons. So they are zeros of the function, which means if we want to decide if something is a factor of a polynomial, one option that we have for how we can do it is just to plug in that value. So if we're checking to see if x minus 1 is a factor of this polynomial, we're really checking to see if x equals 1 is a root of the solution. So let's plug in f of 1 and see if it equals 0. So 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. That's going to give me 1 cubed is 1 times 2 is 2. 1 squared is 1. 2 times 1 is 2 minus 3. So I see I'm going to have 2 minus 1 is 1 plus 2 is 3 minus 3 is 0. So what does that mean? It means that x minus 1 is a factor of this function, is a factor of f of x. All right, let's try that again. Again, this is just one way that we can check. If we want to see if x plus 2 is a factor, what are we checking? We're checking f of negative 2 to see if at negative 2 it would be a factor. So when I plug that in, I'm going to get 2 times negative 2 cubed minus negative 2 squared plus 2 times negative 2 minus 3. Again, just substituting it in x's position. Negative 2 cubed is going to be negative 8 times 2 will be negative 16. Negative 2 squared is 4. That's negative 4. Negative 4 minus 3. So that's going to give me not 0. Like, I don't even care what it is. I can quickly see that it's not going to be 0. So therefore, it's not a factor. It's not a factor of our function. Okay, so our factors are going to be zeros. When we plug them in, we're going to get 0 for our y value. Okay. So since this is that same equation we were just working on, it says since x minus 1 is a factor of our polynomial, we have two ways to find the factored form. So we know x minus 1 is one of the factors, and we want to see what's left when we factor that out. Okay, so we can either do long division, which always works, or we can do synthetic division, which only works with linear factors. So let's take a look at that. Let's try long division first. So our polynomial is 2x cubed minus x squared plus 2x minus 3. And we're going to divide that by x minus 1. Okay, so here when we're doing synthetic division, long division, make sure you focus on the first term. How many times does x go into 2x cubed? And what we're asking there is what would you multiply x by to get 2x cubed? And I'd have to multiply it by a 2 and an x squared. So x times 2x squared would make 2x cubed. So x goes into 2x cubed, 2x squared times. Now notice that I wrote that above my x squared term. Okay, now we multiply it by whatever we're dividing by. So 2x squared times x is 2x cubed. 2x squared minus 1 is negative 2x squared. Okay, and now we subtract that from the line above. Again, this works just like your long division did when you were doing it with numbers. Again, you can try it with numbers first if that makes you more comfortable, but it works exactly the same. So we subtract that from the line above. That changes the sign on each term. 2x cubed and negative 2x cubed canceled each other out, just like we knew it would. And then 2x squared minus x squared leaves me x squared, and I bring down the next term. So now I'm focusing on x squared plus 2x, and I want to know how many times x goes into it. So x goes into x squared x times, because I would have to multiply x times x to get x squared. Now when I distribute it, I have to distribute it by whatever we're dividing by out front, so both terms here. So x times x is x squared, x times negative 1 is negative x. Okay, now I've got to subtract that from the line above, which is going to change the sign on each term. X squared minus x squared cancels each other out. 2x and x is 3x, and I bring down the next term. How many times does x go into 3x? It goes in 3 times. So I'm going to put that above my constant. Now I'm going to multiply it by the expression out front. 3 times x is 3x. 3 times -1 is -3. When I subtract that from the line above, -3x and 3x cancel, -3 and +3 cancel, and I have 0 left. What does that mean? That means my remainder is 0, which means it divides in evenly. If we did not get a remainder of 0, it would not divide in evenly and wouldn't be a factor, okay? But we knew this was a factor already because we had checked f of 1 and found that it was 0, so we knew that it would be a factor and would divide evenly. Okay, so that means the rest of our polynomial is 2x squared plus x minus 3. When I factor that out, x minus 1 times 2x squared plus x minus 3 will give me our original polynomial. So we can do long division. We've been doing long division since elementary school. Looks a little different with x's in it, but works exactly the same. Okay, so now let's try synthetic division. If we're looking for linear factors, and here we are, x minus 1 is a linear factor because it has a power of 1, we can do synthetic division. If x minus 1 is the factor, what root are we checking? We're actually checking the opposite sign, +1. Okay, it's x minus r, so r is actually 1. Okay, so what we need is we need the coefficients of each term of the original polynomial. And if any degree of x is not represented below the leading power, then we'll have to represent it with a 0 in our list of coefficients. So I have 2x cubes, I have -1x squared, I have 2 plain x's, and then I have my constant. So check, I've got x cubes, x squared, x's, and constant. Everything's represented, so we don't need any of those 0 placeholders. For synthetic division, we bring the first term down as is, that's 2, and multiply it by our number here. So 2 times 1 is 2. I combine, that gives me 1, and multiply it by our root. 1 times 1 is 1, combine, that gives me 3. Multiply it by our root. 3 times 1 is 3. -3 and 3 is 0. This last term I always box out, and that's our remainder. Now, our remainder is 0, which means it divided in evenly, and we expected that because we knew x minus 1 was a factor of this polynomial. These numbers that we have in front here are the coefficients on the remaining polynomial. Now, this was a degree 3 polynomial when we started, and we factored out an x minus 1, a linear factor. So the remaining polynomials are just 1 degree lower. So this is going to be 2x squared plus 1x plus 3 is our remaining polynomial. We factored the x minus 1 out, and that's our remaining polynomial, which you see is the same as we got when we did long division. More than one way to work a problem. Correct work will give us correct answers. Okay, so you'll have either approach to work. Synthetic division tends to be faster if it's linear factors, but we can't always do synthetic division, so we've got long division as a tool in our toolbox as well. Okay, so let's talk about rational zeros. P is all factors of the constant, and Q is all factors of the leading coefficient of a polynomial. Then P over Q is the list of all possible rational zeros. Now, this might seem like a kind of simple idea, but this is a huge help to us because instead of having an infinite number of numbers that we have to check and see if they factor into a polynomial when we're trying to find its factors, here we have a finite list. And even though some of these lists might be longer than you like, it's still so much shorter than the list of an infinite possible number of possible factors. So let's see how this works. As a hint, once you get this list of all possible rational zeros, you'll want to start with the lowest possible whole numbers because whole numbers are easiest to work with when checking to see if a particular possibility is a factor. And then as a reminder, if a factor works, try it again because it might have a multiplicity other than 1. It might be a factor more than once. Okay, so let's see how this works. So P is all the factors of our constant. So to remind myself which one is P and which one is Q, I remember I circled this at the beginning and I have to drag it to the front. That's always where I'm going to start. So -6 from the back comes all the way up. It's the first thing we're looking for. So what are all possible factors of 6? That'd be plus or minus 1 and plus or minus 6. Then plus or minus 2 and plus or minus 3. Okay, and so I do the first and last, 1 times 6, 2 times 3, and when there's no factors in between, you know you've got the complete list of factors. Now, I did plus or minus because we could have been doing positive 1 times negative 6 or negative 1 times positive 6, so we've got the plus or minus options there, and we'll always have the plus or minus options because even like with our q here, the leading coefficient is q, so that's 2. Even though we're looking for a positive number, it could have been plus or minus 1 or plus or minus 2, because negative 1 times negative 2 would make positive 2 as well. So we'll always do the plus or minus on the options. Okay, so let's put those together to get the list of all possible factors. So our list of all possible factors, where each of our p factors is a possible numerator and each of our q factors is a possible denominator. So we're going to start by putting all of the numerators over the first denominator. So that's going to look like plus or minus 1 over 1 is 1, plus or minus 2 over 1 is 2, plus or minus 3 over 1 is 3, plus or minus 6 over 1 is 6. And then let's go put them all over the second denominator, which is 2. So that would be plus or minus 1 half, plus or minus 2 halves, which is 1, which we already have represented, plus or minus 3 halves, plus or minus 6 halves, which is 3, which we already have represented. So this is our new list of all possible rational zeros. Every rational zero, which again is a zero that can be represented as a fraction, is on this short list. And that's so much better than just thinking any possible number out there might be a possible factor. So super helpful to us. Okay, now they want us to actually use that list and find the rational zeros. So we're going to start with the lowest possible whole number, which is 1. So if I try 1, I need my polynomial there. I need those coefficients. So we said that was 2x cubed, 11x squared, negative 7x, and negative 6. So I just need the coefficients. Bring the first term down, multiply it by our root. That's going to be 2. That'll be 13. Multiplied by 1 is 13. Combine, that's 6. Multiplied by 1 is 6. And ding, 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 we got a winner right off the bat. Okay, so it does equal 0. So that means that we're down to x minus 1 times 2. Now it's 1 degree lower. So this was x cubed, so now it's 1 degree lower. So that'll be x squared plus 13x plus 6. Okay, now I could keep going with this list of possible factors, but as soon as we get it to something that we can factor by hand, we want to switch and factor by hand. Our existing factoring tools are faster, so let's try finishing that off by hand. I know that 2x squared is going to break down to 2x and x. Okay, so then my factors that need to combine to make 13, so I would have, that would make 2x squared, 1x, and 12x makes 13x, and 1 times 6 is 6. So there are our factors. Now they said to find the rational zeros, so those zeros are going to be x equals, we want to go in order from smallest to largest, negative 6, negative 1 half, and positive 1. And again, that's just setting the factors equal to 0 and solving for them. Most of you will be able to just do that in your head. So those are the actual rational zeros of this function. Okay. So let's try that again for a little practice. So here, my p-value, remember I said grab that constant from the end. That's what we're going to start with. Okay, so that's how I remember which one's p and which one's q. So 48, so it's going to have a much longer list of factors. So we're going to have plus or minus 1 times plus or minus 48, plus or minus 2, and that would be plus or minus 24, 2 times 24, plus or minus 3, and that'd be 16, plus or minus 16, plus or minus 4, and that would be 4 times 12, so plus or minus 12. 5 doesn't divide in, plus or minus 6 times plus or minus 8, and I'm lucky I had just enough room to squeeze it in there. Okay, so there's no 7s in between and doesn't factor in, so then we know that's the complete list of factors. Okay, so let's look at q. The leading coefficient is 1. That's nice to have one that's easy. That's just plus or minus 1. So each of those possible numerators over our only possible denominator gives us a list of possible rational zeros of this function of plus or minus, and again, all of them over 1, it's going to look like a repeater of our p factors, but it's really p over q. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 16, plus or minus 24, and plus or minus 48. Okay, so now we want to find the actual rational zeros. They asked us here to graph this. We'll hold that as an aside and do that once we find the rational zeros. Okay, so let's start with our lowest possible whole number. So let's try 1. Our leading coefficients on our polynomial are 1, -1, -4, 8, and -32. Okay, -32. And then positive 48. Okay, now always double check to make sure you don't need any placeholders. I've got my x to the 5th, x to the 4th, x cubed, x squared, x, and a constant. So we're good to go. Okay, so first term comes down as is, multiplied by our root, combine, multiply 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 by our root. Okay, and all that's important to me here is that it's not equal to 0. That's not equal to 0, so that is not a root. Now, when I check for my next one, I'm going to try -1. So I'll check the positive and the negative. I've got my same leading coefficients because we weren't able to factor anything out. So it's still 1, -1, -4, 8, -32, and 48. Okay, so let's try -1. So bring it down, multiply by -1, that gives me -1, combine, multiply by -1, combine, gives me -2, multiply by -1, combine, multiply by -1, combine, multiply by -1. And again, it's not equal to 0, so it's not a root. Now, you're never going to have to go more than like 4 or 5 roots in before you're going to find one. And so just try to remember it's faster than synthetic division and better than an infinite number of possibilities. So now I'm trying positive 2. Again, my leading coefficients are the same as they were the first time because I haven't factored anything out. So that's 1, -1, -4, 8, -32, and positive 48. So let's try this. Okay, so I'm going to bring my first term down as is, multiply by 2. Combine, multiply by 2, combine, multiply by 2, combine, multiply by 2, combine, multiply by 2. Ding, 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 we have a winner. The remainder is 0, the remainder is 0, and so it checks. Okay, that means that this is a factor. Okay. Yay, that means x minus 2 is a factor of the polynomial. And what we have here are the coefficients on the remaining polynomial. Now, I'm not going to go ahead and write that in factored form yet because we need to keep going. We need to find additional factors because we still have 1, 2, 3, 4, 5 terms in our polynomial. And so to try it, we said next we're going to try a factor of 2 again, checking in case it has a multiplicity of something other than 1. Now, the nice thing is you've already factored out x minus 2. So these coefficients on the remaining polynomial, this remaining polynomial is what we're now dividing out and working with. So I bring the first term down, multiply by 2, combine, multiply by 2, combine, multiply by 2, combine, multiply by 2. And ding, 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 we have another winner. We get a remainder of 0, which means that x minus 2 is a factor, again, with a multiplicity of 2. So now we're down to x minus 2 with a multiplicity of 2 so far. We don't have it fully factored, so that may change. But our remaining polynomial, these are the coefficients here. Now, we took out an x to the 2nd power, so our degree is 2 degrees lower than our original. And so we've got, and you can also count from the back, if 12 is your constant, then that's your x squared, and x cubed. So this is going to be 1x cubed plus 3x squared plus 4x plus 12 is the remaining polynomial after we factor out x minus 2 twice. Okay, so let's go ahead and see, using our other factoring tools, if we can finish factoring that by hand. As soon as you get down to 4 terms, I recommend that you try factoring by grouping. It won't always work. If it doesn't work, then you can just keep going with your list of possible rational zeros. But let's see if it does work this time. Okay, so that's going to be x minus 2 quantity squared factored out. And then this is going to break down to, that would have an x squared in common for the first 2 terms, plus, if I look at the second two terms, they have a 4 in common, which leaves an x plus 3 out. Okay, and remember, when we're doing factoring by grouping, it's only helpful to us if we have the same thing left behind in each group. So in the first two group together, the first two group together, and the second two group together, that when I pull out their common factor, in the first group it was x squared, in the second group it was 4, that I have the same thing left behind. Because what we're going to do in the next step is we're going to pull that x plus 3 out front. Okay, so we pull the x plus 3 out of those two terms. That leaves me x squared plus 4. Okay, now I did start an extra parentheses here, but I don't really need this one right there, so I'll go ahead and take that out. Okay, when I pulled the x plus 3 out, that left an x squared in the first term and a 4 in the second. Again, if you need practice with factoring by grouping, you can Google and get lots of extra practice. Okay, now, is this fully factored? If I take a look at this x squared plus 4, remember when we take our factored form and generate our solutions, which I believe is what they asked for, right? Do they want us to find all the rational zeros? Okay, so they want all the rational zeros, and so that's going to be x equals -3 and +2. Okay, why did I not get any additional factors from this other one? Remember, we set those factors equal to 0 and solve for it, and so that would give me x squared equals -4. And of course, if I take the square root of both sides, you pick up the plus or minus option, but here we have square root of a negative, which does not generate any, no real solutions are generated by that. Okay, so far we're still just looking for real rational solutions. So this is fully factored here, and these are our rational zeros of this function. Okay, they did ask us to graph it, so let's give that a try real quickly now that we have it in factored form. So we knew this was a degree 5 equation with a leading coefficient that was positive. Okay, so its degree was odd with a leading coefficient positive, so odd and positive means down, up, and behavior. We have factors at -3 and +2. And again, you only need to put those critical values on the number line for me. And let's see where our y-intercept would be. So remember, for the y-intercept, x is 0. So anywhere we're on the y-axis, x is 0. So I'm just going to substitute 0 in for x here. So that's going to give me that'd be 0 minus 2 would be -2 squared, 0 plus 3. 0 squared is 0, plus 4 is 4. Okay, so that'd be -2 squared is 4 times 3 times 4. So 4 times 3 is 12, times 4 is 48. So when x is 0, y is going to be up at 48. Again, we'll just put that critical value on there. So here we actually will know where it crosses the y-axis. Okay, so let's take a look at those factors. -3 had a multiplicity of 1, so I'm just going to cut straight through -3. -2 had a multiplicity of 2, so it's going to bounce. So I know that somewhere between here and there, and I'm not sure where it happens, I need to cross that y-intercept, bounce at 2, and connect to my end behavior. Now, I say I don't know where it happens. This is totally a rough sketch, because until we get to our calculus quarter, we won't know how to find where that direction change happens. So it's a sketch. That local max there is that cannot be determined right now, but we will be able to determine where it falls later. So there's an idea of what your sketch might look like.